is an awesome conference. I'm really excited to be here. So today, I'd like to talk about some of the work that I'm doing in StatSet. In our group at UC Merced, we do a lot of incompressible flow problems, mainly multi-phase flow type of things, where we're looking at oil and trains and stratified flows. But one of the things that we do to actually represent these multi-phase flows is use level set methods. Right, when you vect these, where you have a potential mass loss. So some of the things I'm going to talk about today are really to try and address these types of problems. So to start, we're going to keep things very simple. Right, we look at just a scalar advection equation, where I think how we're going to move along that method across the domain. But again, these type of methods, right, we could apply it to like a self-advective type of thing, right, where we're solving Navier-Stokes. But so there's kind of two main issues to do this. First, you can kind of do the finite difference style, where you do forward upwind type of method for a boiler with the upwind scheme. Right. So when you do this, you run into CFL considerations. Right. If you want to have, say, like a Goodenough style approach, you're going to be limited to a CFL half or less, depending on what your mesh looks like. And that's going to be based on kind of the smallest element that you have. Right. So a different form of doing this, right, is to use kind of the Lagrangian form. But when we do this, right, we get these kind of really cool properties that pop up, right? So for our material derivative, right, you see that phi is constant along its characteristics. And then we also get a characteristic equation for the velocity. Basically, what we're going to use to solve this equation backward in time. So for forward Euler, using an upwind type method, right, our stencil looks a little bit like this, right? We use the previous time, right, to update the new time. For the Semi-Lagrangian approach, we treat this in a little bit different way. We do say, okay, if we follow our particle backward in time, right, what does it look like at that previous step where we have known information? Like, we know that our solution is constant along these characteristics. So if we travel backwards, we figure out where the polygon lies. We can just interpolate to this point. And by doing this, right, we kind of get rid of the typical CFL limitations that we have, right? So the pros, right, if we're doing this for a linear problem, right, we have unconditional stability, right, and there's no CFL restrictions. In fact, right, we can even get better accuracy if we increase the CFL, provided we can interpolate well enough. Cons, this is not strictly conservative, right? So if we're solving something where we want a deep observation and we've lost that, that's kind of a bummer, or it's a deal breaker in a lot of cases. The other problem we have is we have to search the grid to find the interpolation point, and we have to interpolate at it, right? So this can be expensive, especially if you have something very complicated. So now let's take kind of a sidestep and let's look at this from, say, a reference map perspective. The reference map is something you see more in solid mechanics, but more recently you've seen it apply to fluid structure interaction problems. This was a paper by Cameron, Rycroft, and Nave a few years ago. And then more recently, right, we've applied this directly to level set methods. My advisor, Maxime Théard, right, kind of took this idea and applied it directly to level set. And the idea here is that you look at your domain, right, in this case, it's B, right, you say, okay, this whole domain is going to deform in some way, right, and that deformation map is this X of T, right, gives you kind of this forward motion. What you can do then is construct a reference map that looks backward in time, right? And essentially is going to follow the trajectories at each point in this domain, right? You look at this in a way that is very analogous to the Semi-Lagrangian method, right? This is how you can start updating your velocity, right? In the context of computational mechanics, right? You can do a whole bunch of things with this map. You can look at the deformations of it, right? You can get stress and strain from this. This is very cool. What we want to do instead is use this map and vect this, right? And then reconstruct our interface via the level set method just by interpolating back at those points. Now, the key to affecting the reference map is it gives you something that's very nice, evidently differentiable. There's a level set function. If you remember these, they tend to have kinks, especially if they're signed distance. So it's a lot more regular. It's really nice to use. So if we think about the Semi-Lagrangian method and the reference map, they're very analogous, right? And instead, what we can say is, okay, if we're going from, say, time tn plus 1 backwards to time tn, right, this map basically just is the set of all these trajectories of all of our points in the domain, right? At Tn plus 2, right, it's basically the set of all the trajectories that go from Tn plus 2 back to wherever our initial configuration was, right? If we look back here, this is our initial configuration. However it deforms, right, we go back to that. So what can we do with that? Now, if we go to, say, a 2D style grid, right, you can say this is our original reference map, right? And then as we move forward in time, right, this map starts deforming, right? We can start tracing the characteristics back, right? And if we look at, say, the local information, right, by taking the determinant of the gradient, right, of the map, what you see is how the size of this map is deforming, right? Is it growing? Is it shrinking? Right? And the idea here is that we can use this information as a metric to then design a method that corrects this deformation. If you remember, if we're vecting with an incompressible field, right, there should be no change in volume, right? This field should be volume preserving. Looking at the determinant of the gradient of the map tells us if this is stretching or shrinking. So if it's not equal to 1, right, we know something's changing. We could use this to then correct our characteristics. Now, one thing I do want to point out, this isn't the actual grid, right? So we're using octant quadtrees, right? And we're finding around some level set function. So our grid looks a lot like this. What you're looking at here is the contours of the gradient of our reference map, right? So it's a little bit different type of thing, just to point that out. So what does it look like when we actually get to, right, look at this metric? So what you can see right here is for a very simple problem. This is like a single vortex problem. It's a canonical example for level set methods. Right on the right, what you see is actually the deviation from the volume preserving space. Right, so this is after a couple time steps. You can see things are starting to stretch and change. Right, we can then use this as kind of the right-hand side for solving a Poisson system. Right, that's going to generate a correction to our field. Right, that correction basically moves where the trajectory are those departure points, in such a way that we're pulling from a volume preserving space. Right, so the algorithm, what this would look like is we start a normal way, right? We vect the reference map itself, right? We then measure the deformation from the volume preserving space, right? Once we have that information, right, then we solve the Poisson problem. We get this correction term, right? And then we can feed this correction term back into the reconstruction of the. And then when we do this, right, what we end up getting is something that preserves maps better. So in particular, if we do it properly, right, we can see that we have kind of a second order mass preservation, right? So what we're doing here is looking at the single vortex example. So basically you have this blob, right? We're vecting this blob in some kind of external velocity field, and you can see it start to stretch, right? And what you see in the background is the actual contours of the characteristic map, the radial. And then over on the right-hand side, you can see kind of our measure for mass loss. So if we have something that's very unrefined, and I guess just to preface this, we're using quad octree grids. So the refinement level is basically 2 to the power whatever is on the bottom. So if we have something that's very unrefined, right, we see that the reference map or volume preserving reference map does a much better job at preserving the mass. And then as we continue to refining, right, we see that this VP RM actually gets second order. Whereas when you have the traditional level set method, you start to see that flattening off. And it's going to end up converging to something that's more like first order. Now, that being said, there's a couple drawbacks. If we go to, say, a very sharp example, like this slotted cylinder, if you haven't seen this before, basically we just rotate this in a field and then rotate back. Look at how the interfaces change. When you do this with just the reference map and you don't do any kind of volume preservation, because the characteristics don't cross, where you can get really good accuracy and you can really preserve these sharp interfaces, right? Which is what you're seeing right here. You preserve this really sharp thing. The traditional level set method ends up smoothing this out. Main reason for this is that when you reinitialize the level set function, right, it has some kind of diffusive effect on the interfaces, so you get some smoothing. But you have the same type of smoothing happen when you're now doing the projection on the volume preserving reference map. So there's some instances where maybe you're not benefiting as much. So again, this was like a really quick summary of what we do. We do a lot more. Again, a lot of this is applied in the context of multi-phase flows. And then, yeah, just to highlight some of my lab mates, right? We do lots of different simulations out of Earth, West. Thank you.
So I spent my summer at the lab as well for my internship with Vladimir, and we worked on advection-based remap for continuous fields like the velocity field in the Lagos or Ale solver. And yeah, the advection-based remap can be interpreted as an advection equation with an additional equation for the mesh movement, where nu is a velocity field. We assume this to not skew the original domain, and we define the velocity field of the mesh by the end node minus the original node. So we basically just take the interpolant, and as we can see here, for example, we have an old mesh which comes from the L solver. We want to remesh. We have quite skewed cells which might influence the time step restriction or similar things. We mesh to a new mesh, and overall we try to hold the like the velocity field, the shape in place, and remap this way. As I said, the domain is not skewed. By this we mean the velocity, the boundary nodes only move along the boundary. So we have this constraint down here, which is quite helpful. Before we go into more detail, let's look at some notation. The first two are pretty standard. We have basis functions. We use continuous high order Bernstein polynomials on a moving mesh. The second one is a grid function, as we all know it. And then we have some index sets. The first index set, EI, is the elements which share the ith node. We have the element stencil and E, so the indices of the nodes that belong to the eth element. We have the global stencil of the ith node, which is Ni. And we have the stencil of the ith node without I itself, and some localizations on elements of those sets. Yeah, so as I said, we can look at the advection-based remap, as the name says, as an advection equation. Owing to the Reynolds theorem, the transport theorem, we can write it as such in the semi-discrete way with a mass matrix and a convection matrix. And looking at an element-based formulation, applying mass lumping and adding element-based artificial diffusion, we obtain a low order method, which we can write like this, because K has zero sums, and we construct D such that this sum here is non-negative, which is given by this definition. And we can show quite easily that this is bound preserving by some convexity argument. So we can write the low order method in a so-called bar state form, where we get this UIE bar on each element, and we can show that these bar states are convex combinations of the element stencil. So by construction, these are within local bounds. And now discretizing with a strongly stability preserving Runge-Kutta method, and looking at a Euler step, we can rewrite this whole formulation such that we can quite easily see that if this is smaller or equal than 1, then we get a convex combination. So basically the Euler stage is a convex combination of the stencil of the old time step, and thus we obtain this bound preservation property. And now we want to recover a high order method We do this by adding antidiffusive fluxes. The first one is the first summand of this antidiffusive flux is to compensate for mass lumping. And the second one on the right-hand side is to reduce the diffusion or counteract the diffusion we've added to construct the low order method. We sum these up to element contributions and add these to the bar state form. And if we replace these antidiffusive fluxes by their limited counterparts and include these in the bar states, we can regain our bar state form with now the limited bar states, the limited high order bar states. And we can apply the same convexity argument if these limited bar states are now between the local minimum and maximum as well. So we can rearrange this constraint to get bounding fluxes for our limiter, for our limited flux. And this is where our limiter comes in. So how do we enforce these bounds for our flux? We use the clip and scale limiter, which is quite greedy. Yeah, the first step, as the name says, we just clip off whatever is too large or too small. So we just greedily clip off the flux. We get these intermediate antidiffusive fluxes. And doing so, we generally are not mass conserving. For mass conservation, we need that the sum over the element contributions is 0. So we define these sums where we just collect the positive and negative contributions. And then we just, in the second step, we scale them such that this identity here is reinforced. And thus we gain bound preservation by the convexity argument under the time step restriction and mass preservation. And finally, we go to some numerical examples. The first one is classic for a linear advection, the solid body rotation, which is not rotating anymore, but instead we remap this onto a quite deformed mesh. And on the top, we can see the initial condition, which is u between 0 and 1. And we can see by remapping that this method is quite accurate. We have good accuracy. We have no oscillations at all. We don't have overshoots at the discontinuities. We have some peak clipping, but compared to other methods, it's quite okay. And if we apply this to the velocity field component-wise in, for example, the Lagos solver and remap from this initial condition, which we gain from the Lagrangian phase, and remap to an optimized mesh, we also see that we have the same profile, like the same velocity profile. It's not deformed. We have a little bit of peak clipping as well, but overall we have no oscillations and a quite stable solution. So yeah, that's basically the idea. Clip and scale, we applied it to advection-based remap. As I said before, we obtained stable and non-oscillatory solutions. We had nice shock capturing without any bounds that are not preserved, and we obtained, or we preserved the shapes of the initial condition quite well. Work in progress at the moment. I've implemented this into the example 9 at like the serial and the parallel version. It's under review at the moment. I need to do a little bit of adjustments, but that's done in like a few minutes. We worked on some boundary penalty terms to enforce the normal boundary of the velocity field in the velocity remap to be 0. So after the remap phase, the boundary nodes don't start moving inwards or outwards of the boundary. And for limiting of this kind, where the stencil gets bigger, the higher the polynomial order is, you need to to go down on subcell limiting to regain higher order, because this limiting procedure is second order max, because it was designed for linear or multilinear elements. So these are my references, and I'd like to thank you for your attention.
Okay, yeah, so hi everybody. My name is Arjun Vijayvargiya. Thanks for joining in. Thanks to the organizers for inviting me. And today I'm going to be sharing some of the work that I did as part of my doctoral research, and it concerns the higher order computation of mean field control barycenters with MFEM. So what are these MFC barycenters? Well, these are a generalization of the classical Wasserstein barycenters, which themselves represent averages of probability densities. So probability densities don't live in Euclidean spaces, right? And to average them in a meaningful way, you need some kind of an appropriate metric. And that's where the Wasserstein metric comes in. And the Wasserstein metric has several different formulations. In particular, there's the Benamou-Brenier formulation that the MFC approach exploits. So this formulation thinks of the densities as fluid dynamical variables that can flow, right? And the MFC approach adds additional terms in this formulation so that effects like reaction and diffusion can be included. So we take this MFC approach, build the barycenter problem, right? And then construct a comprehensive computational framework that utilizes higher order finite elements to accurately solve these barycenter problems. I want to talk a little bit about the Wasserstein metric itself, the modified one that we built. So we have a distance function from M to the N, cross M to the N to positive reals, where M is the space of probability densities, right? And this gives us a distance between two vectors of probability densities, in this case, rho 0 and rho 1, which is obtained by solving this optimization problem. So the goal here is to find control variables, rho, M, and S, that minimize a certain sum of energies in such a way that the control variables themselves satisfy a set of reaction diffusion equations, right? And if the mobility functions V1 and V2 are positive and concave, then this is going to be a nice convex optimization problem with linear constraints. And I want to point out here that if V1 of rho I is just rho I and V2 of rho is 0, then we recover the classical Wasserstein distance formulation, right? And there's a reason why I gave this distance function in terms of vectors and not scalar densities, because from here we can directly construct the barycenter problem by simply considering rho 0 to be a collection of all the initial densities whose barycenter we wish to compute, and rho 1 to be a density vector, all of whose components are this unknown terminal density cursive rho, right? And if we set this cursive rho, if we include it as another control variable in the optimization problem, then we recover the barycenter problem. Because at optimality, this cursive rho is going to converge to the Wasserstein density, the barycenter density, right? So now we have formulated the problem. We need a way to solve it, right? So first we want to go to the unconstrained version of this problem. We'll introduce Lagrange multipliers and enforce the PD constraint using the Lagrange multiplier. Once we have this, we are going to integrate the second integral by parts, right? So that we can transfer the derivative information onto the Lagrange multiplier, and so that the cursive rho term is going to pop out as a boundary contribution, right? And then we just introduce some additional notation so that we have simplicity of presentation. So at end of the day, we're going to be solving this saddle point IMSOV problem, where the Lagrangian takes this form, right? But still infinite dimensional, right? And to be able to put it on a computer and to solve it, we need to discretize it. So we mesh our domain, right? Our space mesh is going to consist of uniform hypercube elements, right? And our time mesh is going to be of uniform line elements, and then the space-time mesh is simply a tensor product mesh of the two, right? And once we have the meshes, we can define the finite element spaces. We'll make use of 3 different finite element spaces. The first one is going to be an H1 conforming space, and this one will be used to approximate the Lagrange multipliers because we need derivative information on those, right? And the other 2 are going to be discontinuous spaces. The W space is, it exists on the entire space-time mesh, and it approximates the flow map rho, the fluxus M, and the source term S. And then we have this another space M that lives on the space mesh on the right time boundary, right? And this is used to approximate the terminal Wasserstein density. So this gives us a discrete version of the problem, so shown in the last form on the slide, right? And still an optimization problem, so we need some kind of an algorithm to solve it. We make use of the primal dual hybrid gradient method. So this is a powerful first order optimization method, which has very forgiving convergence criterion. It consists of 3 different steps. The first one is a proximal gradient ascent for the Lagrange multipliers. The second one is a simple interpolation, and the third one is a proximal gradient descent for the physical variables, right? And so we just alternate between these until a certain convergence criteria is met. And what's so cool about our framework is that the first step actually turns out to be a simple Poisson solve for each Lagrange multiplier. It has some cross terms, so we do a Gauss-Seidel type splitting to break them, right? And then sequentially solve for each Lagrange multiplier. The second step is a simple pointwise update. And the third one, because we use a combination of Gauss-Legendre quadrature for computing the integrals and nodal Gauss-Legendre basis function for the L2 spaces, the step 3 actually turns out to be nonlinear solves for the Wasserstein barycenter density and the physical variables at each individual degree of freedom, right? So we just have to solve this minimization problem separately at each integration point. So we solve these using MFEM. As I said, my mesh is going to be tensor product spacetime mesh. We define our custom classes for the assembly of the linear systems that are involved, right? And for defining our quadrature functions and operating on them. And once we have these, the elliptical problems are solved. For the Lagrange multipliers are solved using the conjugate gradient solver in MFEM, and we use a geometric multigrid preconditioner. And the nonlinear optimization for the physical variables at each degree of freedom is done using a C++ implementation of the Brent method, which I believe uses a combination of bisection method and golden section search. Right, and as I'll show in my next slide, the problems that we tackle are large problems in 3D, so they cannot be solved like on a laptop, right? So we use MFEM's MPI-based parallelism and run the code that we develop in an HPC environment. So here are some of my numerical results, right? The first problem that I tested this on is computing the barycenter of 3 Gaussian species in 3D. The barycenter is actually a single Gaussian whose center is, I've shown it here, whose center is located at the centroid of the triangle formed by the centers of the initial Gaussian species. I also have this convergence curve. The purple one shows the convergence of the PDHG algorithm as a function of iteration count, and the green one shows the convergence of the L1 error of the solution, because for this problem, we have an analytical solution available, and we see stable convergence of the PDHG algorithm. The second one was this 3D shape interpolation experiment, right? So I have 2 3D objects, and the optimal map provides continuous interpolations between these 2 species. So this is kind of misleading, because what I'm actually computing is flow maps that flow torus and the bunny into the barycenter, but the way I have displayed it is I just combine the results of those 2 flow maps, and I have a continuous interpolation from the torus to the bunny. And then just to show that the computational framework itself is robust and can also handle surface meshes and do computations on surface geometry, I computed the barycenter of 4 indicator functions on this dinosaur mesh. So this is not a volume computation, this is just surface computation. I have indicator functions on, so one of them is on the head, 2 on the feet, and 1 on the tail. And when the PDHG algorithm converges, it gives me some kind of distribution localized around the abdomen. So yeah, that's the end of my presentation. If you found this work interesting, I've listed some of my other papers. If you have any other questions, just reach out to me. Thank you everybody for listening.
Okay, perfect. Good afternoon, everyone. I am Yizhong from Tsinghua University. Today, I'm happy to have a chance to present our work on MFEM workshop. It is about FP16 acceleration in structure multiple preconditioner. Since time is limited today, I will be skipping or going over some of the technical details very quickly. If you're interested, you can check out our paper here for a more in-depth understanding. In machine learning and AI, we have seen a trend towards lower precision, but they are not so prevalent in scientific computation. where applications usually have higher precision requirements. Many of scientific simulations rely on numerical solution to PDE problems, and the most essential part will be a linear solver. Among the most common mixed precision strategy to accelerate linear solver is to use a lower precision preconditioner for FP64 solver. Among various preconditioners in iterative methods, we focus on Melgrid because of its significant values and inherent challenges. This slide explains why we choose Melgrid MG, because it has optimal computational complexity. It is widely used. It already has some theoretical foundation for mixed precision, and most importantly, from the practical view, the lower precision in MG can bring about greater speed ups than other one-level preconditioners. But applying FP16 in MG for real-world problems are obviously challenging. FP16 has a narrow range and limited accuracy. However, the values in real world are having large spans, wide gap, and matter scales. Meanwhile, the matter level framework, complicated procedures of MG increases the vulnerability to numerical hazards. Here we have a quick review of some previous work. Most popular AMG libraries still lack mixed precision support. And for a long time, most practices use only FP32 as the lowest precision in MG. Utilizing half precision is more scarce. Jinko is a very recent work, and the existing work still lack guidelines in how to choose the best configuration. So in our research, we summarize 4 guidelines and indicates only some combination of precision are worthwhile to try. We present algorithm on how to adapt the setup and solve phases of MG to FP16, and we also show how to avoid the precision conversion overhead in implementation. By putting them together, we could obtain more prominent speedups. MG is set up once and applied iteratively, so its total time consists of 3 parts: the setup time, the single iteration time, and the number of iterations. The lower precision effect can reduce the single iteration time but may increase the number of iterations. So the essential rule is to pursue a balance or a trade-off between performance and convergence. The first guideline is to eagerly convert matrices to FP16. It is based on the observation that matrix A is always the hotspot of storage. Statistics of matrices indicate that large values of percent A are very common. It inspires us to reduce the lower bounds of memory access volumes of matrices by FP16. The second guideline is to use FP16 from the finest possible level. Theoretically, there will be 9 power n possible combinations for an n-level MG. There will be the very large searching space, but we think that only very limited choices are worthwhile. This is based on MG's feature of grid and operator complexity. Our statistic of 60 MFEM cases indicate that low complexities are very common, implying that most overheads are actually on the finest level. A common mistake is to use lower precision on coarser levels. That's a misleading way. I think that could not bring about satisfactory speedup. So just try FP16 from the finest possible level. The guideline 3 says we should avoid vectors in FP16. Different from the matrix A that is given and static, the vectors are changing dynamically. It is difficult to predict which element may overflow or underflow sometime. Therefore, we should keep the precision of vectors not lower than FP32, and that only introduces a limited performance impact. The final guideline is to prefer structured matrix format that do not use per element index arrays. This is based on the observation that integers in large matrices are difficult to compress, but they are actually necessary in unstructured formats. In contrast, some formats without integer arrays are more preferred. They can be used in structure or semi-structure specific MGs. So to enjoy FP16 speedups, applications had better consider structural grids to discretize their PDEs whenever possible. So the above 4 guidelines instruct the following algorithmic designs. They are summarized here. The following slides will contain variables in different colors, meaning with different precision. I would like to declare them here. The iterative precision is labeled in red. Usually FP64 or 32. It is determined by users' applications. The computation precision of preconditioners usually is labeled in blue, is usually as FP32, and the storage precision labeled in green is usually FP16. The first algorithm is named setup then scale. It is used in the setup phase. The key idea is to prevent FP16 from interfering with multi-level effects. The triple measure product plays an essential role in AMG because it builds up the connection between the consecutive levels. It is sensitive because of the entire chain throughout all levels, and thus very vulnerable to FP16. So as you can see here, a normal setup is completed first in high precision, including the triple measure product here, then followed by scaling and truncation. It is worth noting that AI and QI in high precision are no longer needed after the setup, so it only brings limited additional memory overhead. Our second algorithm is recovery and rescale on the fly. It is used in the solve phase. In this phase, everything is normal about iterative solvers. As you can see in this algorithm, nothing is special here. Actually, the special treatment is inside the AMG. Inside the AMG preconditioner. The key idea is to leverage FP16 in storage of matrices to reduce memory access volumes. You can see in this algorithm that nothing in iterative precision is inside the AMG. The matrices are stored in FP16, labeled in green here. They are FP16 and they need to be restored before involving in SPMV or SPTRSV. On the fly means that the operation does not explicitly maintain the FP32 data AI. Instead, the data of FP16 is retrieved, promoted to FP32, used to calculate, and then discarded. Here we have some practical remarks about our setup then scale strategy versus the opposite. Due to limited time, I have to skip them here. The conclusion is that the setup then scale strategy is better than the opposite, and additional overhead of QI is cost efficient. For the next part, we will focus on the additional overhead of precision conversion in the kernels. Our implementation is based on structure-specific AMGs that use the AOS format to store the matrices. In this format, the non-zero entries within a row are stored contiguously. So when both the matrix and vectors are stored in FP32, everything is okay. But things change for FP16 because the data preparation is one load and one activity instruction for each 2-byte entry. It has 4 times higher arithmetic intensity, and we could observe an evident drop of bandwidth efficiency. So we need SIMD instruction to amortize the FCVT overhead. But the commonly used AOS format inhibits effective vectorization. So we need to transform it into SOA format to utilize SIMD instruction. And after that, we could observe the bandwidth efficiency recovers with this transformation. The next part is experiment. We conduct evaluation of 8 problems covering scalar and vector type PDE, and covering different domains such as radiation, petroleum, atmospheric, and linear elasticity. These problems have distinct numerical features as summarized in this table, whether their range is out of FP16 range and how far they are away from the representable range of FP16 and how strong their anisotropy is. And our experiment is based on StrMG. This is a structural algorithm developed by our team, but the techniques in our research are universal and can also be applied in our AMGs. We'll present the result in a local to global perspective. First is the algorithm effect. We select 5 problems to examine the algorithms, and they feature distinct numerical ranges and distributions. We can see that FP16 delays convergence in complicated problems, but our setup then scale strategy is always better than the opposite in complicated problems. For the mixed precision kernels, after using our SIMD implementation, the performance can be very close to the theoretical upper bounds. In the end-to-end experiment, we could see that the setup then scale strategy introduces only limited set of overhead as shown by these blue columns. And finally, strong scalability is tested. We must admit that mixed relation weakens the scalability because using FP16 storage will increase the communication proportion. But in most cases, leveraging FP16 at the cost of scalability is still worthwhile. The degradation is particularly evident in small size problems due to SIMD underutilization. And there are some interesting discussions, but I have to skip them due to limited time. You can find them in our article. To conclude our research, I would like to say that all is about balance between performance and convergence. And to pursue this balance, we present guidelines, algorithm, and corresponding implementation. The guidelines and algorithms also apply to unstructured algorithms. And kernel implementation can be ported to many structured and semi-structured specific MG. And that's all of my presentation. Thanks for your listening and welcome any questions.